so what we were discussing was this problem. Hope you remember. Now here in the first case, I didn't consider this at all. It was like this. So I then inserted such a dependent source and I asked whether you are getting these columns correctly, this row correctly, the entries of this row. Yeah, so I told you this is A11, A12, A21, I mean A12, A13. This is A21, A22, A23. This position is A31, A32, A33, which means A11 means all those resistors connected to the first mesh and so on and so forth. We discussed that. Now coming to the last column, A31. Usually you would have written only A31 means whichever is resistor which is common to the mesh current or mesh loop 1 and 3. You would have written only 12 had there been no dependent source. But because of this dependent source, 4 I0 is given. What is I0? I0 was this current. Which was I0? Didn't I give you I'm sorry, IA, I0 is this current. Okay, I0. That I0, or as you know, I had given you this is I1. I0 is I1 minus I2. I0 is I1 minus I2. Let me make it more clearer. Okay. I0 is equal to I1 minus I2. This is I0. I1 minus I2. Okay. So 4 I0 will be 4 I1 minus 4 I2. Now coming back to my column, there I am checking about elements. So this is as good as, this dependent source is as good as a resistor 4 carrying current in one direction and carrying current in another direction, minus I2 and carrying current I1 and minus I2. So whenever I am concerned with 3 I1, the position 3 I31, A31 means 1, this 4 also should be taken into account. So more 4 here, minus 12 plus 4, I'll get it as minus 8. That is how I ended up with this minus 8. Now coming to position 3, 2. Again, I am having, had this been the original circuit where I didn't have this independent source, so dependent source, I would have written only minus 4, 4, that is 3, because it is minus, I am putting minus because it is common. Minus 4, I2 in this direction and I3 in this direction. So minus 4 I would have written. But here, because I have 2 current I2 also coming in, I will be putting minus 4 of this resistance plus minus 4 of this independent source. So it becomes minus 8. A33 remains the same because I don't have an I3 here, only I1 and I2. So the dependent source has brought in change in I1 and I2 only. Gautam, did you understand, Gautam?
Yes, ma'am.
Did I confuse you or did you understand? Should I repeat this once again?
No, ma'am.
Gautam? Is that okay?
Yes, yes.
So these problems are okay. These by inspection, just like that, because I told you can put it as A11, A12, A13, etc. But this problem will not come if you are writing the whole equations and then from the equation if you are writing the matrices. In the long run, it is always better to just by inspection, just looking at those, you can put A11, A12, A13, so on. Otherwise, you'll be writing mesh equations for mesh 1, mesh 2, mesh 3, and then rearranging the terms so that you have terms in I1, I2, I3, and then filling up the matrices. There are two ways. One is you write the matrix equations, then you fill up the matrices, matrix equation. or directly write the matrix equation. This kind of a problem that I was discussing, this kind of a difference or this kind of a uniqueness comes only when you are writing a matrix equation by inspection, and whenever there is a dependent source or a dependent source for I not dependent source അവിടെ ഉള്ളത് കൊണ്ടാണ് ഇങ്ങനെ ഒരു ഡിഫറൻസ് വന്നത്. അപ്പൊ രണ്ട് രീതിയിൽ എഴുതാം. Some of you I feel may be comfortable with Malayalam, so I'm just repeating for their sake alone. രണ്ട് രീതിയിൽ എഴുതാം. മെഷ് കറന്റ് 1, മെഷ് I1 മെഷ് I2, മെഷ് കറന്റ് I2, മെഷ് I3 എന്ന് വെച്ചിട്ട് മൂന്ന് മെഷിന് സെപ്പറേറ്റ് ആയിട്ട് മെഷ് ഇക്വേഷൻസ് എഴുതിയതിന് ശേഷം മെട്രിക്സ് ഇക്വേഷൻ ഫിൽ ചെയ്തിട്ട് ക്രൈമേഴ്സ് റൂൾ ഉപയോഗിക്കാം. അല്ലെങ്കിൽ ഞാൻ ഇപ്പോൾ പറഞ്ഞതുപോലെ A11, A12, A13, A11 എന്ന് പറയുമ്പോൾ മെഷ് 1 കണക്ട് ചെയ്തിരിക്കുന്ന എല്ലാ റെസിസ്റ്റൻസും, A12 എന്ന് പറയുമ്പോൾ മെഷ് 1നും മെഷ് 2നും കോമൺ ആയിട്ടുള്ള റെസിസ്റ്റൻസ് വിത്ത് എ നെഗറ്റീവ് സൈൻ ഇഫ് I1 and I2 ആർ ഇൻ ഓപ്പോസിറ്റ് ഡിറക്ഷൻ, ഇങ്ങനെ ഫിൽ ചെയ്തിട്ട് വേണമെങ്കിൽ ചെയ്യാം. ചെയ്യുമ്പോൾ ഇങ്ങനെ ഒരു ഡിപെൻഡന്റ് സോഴ്സ് വരുമ്പോൾ മാത്രം ശ്രദ്ധിക്കണം. ഇൻസ്പെക്ഷൻ വഴി ജസ്റ്റ് നേരിട്ട് മെട്രിക്സ് ഇക്വേഷൻ എഴുതുകയാണെങ്കിൽ ഉള്ള കാര്യമാണ് പറഞ്ഞത്. ഓക്കെ, now one more thing. Okay, now after mesh analysis, the next thing is node analysis, node voltage analysis. Node voltage analysis. Okay. As before, we'll go directly into a problem and discuss what is being done within that, not the theory and then go to the problem. So, calculate the node voltages. Calculate, write down, calculate the node voltages in the given circuit. Calculate the node voltages in the given circuit. The circuit is this. Ohm, 4 ohm, 6 ohm. This is 10 ampere. This is 5 ampere. And you are asked to find the voltages at node 1, that is V1, and node 2, voltage V2. You are asked to find out these two voltages. Now, let me, they have not given you any current. You have they have given you current sources, but not written the current through all the elements. But let's write the elements. Because this is 10 ampere. Okay, then I can have let me put this as I1. Because in the textbook it was this, I put, that's all. You can put I1 wherever you want. I1, which means this is I1, 5 ampere, which is the same as 5 ampere, okay. Then I can put an I2 passing through 4 amperes, I3 passing through 2 amperes, and an I4 passing like this, and an I5. Actually, I don't require all these currents. I'll tell you why later on. Okay. Now, one thing that you have to note here is that when it comes to node voltage analysis, I have put only current sources, 10 ampere and 5 ampere current sources, no voltage source is given. Whenever you have node voltage analysis, you are going to apply Kirchhoff's current law to the nodes 1 and 2. And when you apply current law, you are given current sources which can directly be put as those currents. When it comes to voltage sources, we'll see in the next class. Okay, now today we'll confine our discussion to those networks which have only current sources. Okay, so let's apply KCL to node 1. Node 1. This. Okay. Current that is coming in is I1. So I1 is equal to I2 plus I3. I1, as you know, is the same as 5 amperes. So 5 is equal to I2. All of you should listen. I'll give you time to write. What is I2? All of you just listen and I'll give you time to write. What is I2? I2 is a current flowing from node 1 to node 2. Node 1 to node 2, I2, which is flowing from node 1 to node 2 through a resistor 4 amperes. So which is at higher potential? V1 is at higher potential. V2 is at a low potential. That is why current is flowing from I2 to I1 to I2. Now, this current, the direction is purely assumed direction. For our calculation, this is enough. I have taken I2 to be flowing from V1 to V2. So long as that assumption stands, I should think that V1 is at a higher potential and V2 is at a lower potential. So how will I write I2? I2 will be V1 minus V2 by 4. Similarly, I3 is the current flowing from V1 through to downwards. So here I will take a reference voltage. This is considered to be 0. This voltage. In node voltage analysis, I'll take a reference node. This node, the whole of this node, this is all the same node. This node is at 0 potential. So when I take I3, I3 is the current flowing through 2 ampere from V1 to the reference node. So I can write this as V1 minus 0 by 2. Hope this is clear to you, all of you. If so, write down this equation and then I modify this equation so that I get 3V1 minus V2 is equal to 20. I just multiplied by 5 or 4 by 4 throughout and I got this equation so that I can get rid of the fractions. That is all. If you have understood this, kindly write the equation at node 2. Now it's 11:17. I'll give you 1 minute and then we'll check with whatever I'm writing. 11:17 in my computer. I'll come back with 11. I'll contact you again at 11:18. Okay, hope you have written. In node 2, check whatever you have written is correct or check whether I am writing correctly. At node 2, if I apply KCL, Kirchhoff's current law, I will get I2 is going to the node, I4 is also going to the node. So I2 plus I4 is equal to I1 plus I5. I hope this is correct. If I am wrong, please correct me. I1 is the current flowing out of node 2. I4 is also, I2 is a current coming onto the node. I4 is also a current coming onto the node. So all those are kept on the left hand side. I1 and I5. I1 is going away. I5 is also going away. So what is I2? I2 is a current flowing from node V1 to V2 through 4 amperes. So V1 minus V2 by 4 plus I4 is 10 ampere. It is coming in 10 ampere. So I can directly write it as 10. is equal to I1. I1 is a current, which is a current source, 5 ampere going out. So it is equal to 5 plus I5. I5 is a current. This current is a current flowing from node V2 downwards to a reference through R, through a 6 ohm resistor. So that is V2 minus 0 by 6. That again I can rearrange the terms and get rid of the fractions, and finally I'll end up with minus 3V1 plus 5V2 is equal to 60. Equation number 2. I hope this is clear to you. Anyone has any doubt here?
No, ma'am.
Okay. Now the underlying point that you have to understand is, suppose you are given a network and you are asked to find out the current through 6 ohm resistor or 7 ohm resistor or 8 ohm resistor, and then they have not mentioned whether it has to be done by mesh current analysis or node voltage analysis. Depending on the type of source that is given, if it's a voltage source that is given, it is always better to go for mesh current analysis, as we did in the previous class. Where if it is a current source that is more relevant, more current sources in that, it is always better to go for node voltage analysis, as we are doing it now. Now, from these two equations, we have to write the matrix equation. Okay. So the matrix equation will be written from these two equations, equation 1 and equation 2. How will I write those two equations? As before, I'm right now, this is case 1 where I'm writing from the equations that I've already written. So this is how I'll get the matrix equation is equal to this. Here, instead of the I1, I2, which I wrote in mesh current analysis, I'll be writing V1, V2. 3V1 minus V2. 3 minus 1, 20. Okay. Minus 3, 5, 60. Minus 3, 5, 60. Now you can use Cramer's rule and find out. What is Cramer's rule? This is delta. You find out the determinant value of that matrix, delta, which I'm not going to do it now because of the time limitation. You have to do it. Delta, as you all will know, will be 3 minus 1 minus 3, 5. That is equal to 3 into 5, 15 minus 3, 12. Delta will be 12. And then I1, or sorry, V1 will be, what you will do is this delta, it is V1. First column alone, you will write it as 20, 60. The other column remains the same, minus 1, 5, divided by 12. That you will get as per the calculations, you will get as 13.33 volt. Similarly, V2 will be the second column changed. Second column will be 20, 60. You will replace by these values. And the first column remains the same, 3 minus 3, divided by 12. Again, delta 12. That V2 you will get as 20 volt. Now, suppose you are asked to find out current I2, or let me write all those things here. Okay, check whether you are getting all these values. Okay, if you are asked to find out I1, as you know, is 5 ampere already given. I2 you will get as V1 minus V2 by 4, which you will get as minus 1.67 amperes. What does that mean? This minus sign, what does that mean? I2 you have taken as a current flowing from V1 to V2. As you, but that was an assumption. This negative sign indicates that your assumption is the opposite, or I2 doesn't actually flow in the circuit. I2 actually flows in the other direction. That is clear from this also, because V1 is minus 13.33, which is lesser than V2, which is 20 volt. That is not a point of concern at all for us. At first, we didn't know which is V1, what is V1 and what is V2. We assumed I2 as being flowing from V1 to V2, but in actual case, it is flowing from V2 to V1 as indicated by this negative sign. It is okay because I2, as in your case, I2 is negative 0.67. Then you can have I3, which is the current here, which is V1 by 2, that is 6.67 amperes. And I4, you already know I4, that is 10 ampere. I5 is the current flowing through 6 ampere resistance, which is V2 by 6, that is equal to 3.33 amperes. So this is how you find out the current using node voltage analysis. So I just want to emphasize this again. The assumption that you took here is not wrong. You had taken it as your I2 is flowing from, say, left to right, but in actual circuit it is flowing from right to left, and hence a negative sign has come. Even if you write it as minus 1.67, you will get the full marks. It is not the concern of marks alone. You have to understand that your assumption is not wrong. You have assumed the current in a direction opposite to that of the actual flow of current. That is all. And that is understood from this negative sign. Okay, that is node voltage analysis. We'll do one more problem and then stop. My eyes is bothering me a little bit. As I told you before, tomorrow you will have class. Your class will be engaged by one of my MTech students, and I have given him all these details. He'll be just going through all the metrics, mesh current analysis, node voltage analysis, all those problems. Make sure that you do all these problems which I have given you. You do some kind of homework and sit in that class. Then it will be easier for you. Okay. The next question is this. Okay. One more problem and then we'll stop. 4 ohm. Then I have dependent source comes in, and okay. In the previous problem, I forgot to tell you something. Let me go to the previous problem once again. One more thing I wanted to tell you. Okay. Even if I don't get time to do this problem, the previous problem, I want to tell you one more thing. This. Okay, 10 ampere, 5 ampere, 2 ohm, 4 ohm, 6 ohm. This was your V1, this was your V2. Now, this I1, I2, that is all. Now, you can write the equation directly. You can, as I told you in the previous section, you can write these, you can denote I1, I2, I3, etc. and write the equation using KCL and then write it from the KCL equation 1 and 2 in our previous case. And then from those equations, you can come to matrix equation, or else you can directly write the matrix equation, as I mentioned in the mesh current analysis also. So in mesh current analysis, we had I1, I2 here. I am writing V1, V2 here. One more thing that you have to remember is in mesh current analysis, what you were doing was a resistance into current is equal to voltage. That is Ohm's law. V is equal to IR. You are writing all values of R and I, then you get a voltage on the right hand side. But here you are concerned with voltages. So what you do is the conductance into voltage is equal to current. That is how you are doing. What is conductance? 1 by R. So 1 by R. So here A11, A12, A21, A22, the positions you have to fill up with the conductances. Okay. So I is equal to V by R, or I is equal to VG. Okay, where G is the conductance. So here I'll be writing A11 will be all those resistances connected to V1, but in the form of conductance. That is 1 by 2 plus this resistance, and the conductance corresponding to this 1 by 2 plus 1 by 4. It is not 1 by 6. Okay, it is not 1 by 2 plus 4 Allah. It is 1 by 2 plus 1 by 4. Then A12, all those conductances which are common to V1 and V2. You have only one, that is 1 by 4. You put a negative sign. Here again A12 is the same as A21, that is minus 1 by 4. And here A22 is the sum of all those conductances which are connected to V2. Which are they? 1 by this conductance corresponding to this resistance and this resistance. So 1 by 4 plus 1 by 6. It is not 1 by 10, remember. And here, which is the current source which is connected to V1 alone, that is V1 alone is 5 ampere. It is coming into the node. Again, V2 will be this 10 and 5 ampere. Both are connected here. 10 is going in. So 10 minus 5. That is again 5. Now, if you calculate V1 using this matrix equation, and if you calculate V1, V2 using the previous equation, they are one and the same. You will get the same answer. This is by inspection. The other was from after writing the equation. From the equations, you arrived at the matrix equation. Similarly, in mesh current also, you can directly write A11, A12, etc. from directly the resistances, or else you can use KVL there, write the equations, and from the equations you come to the matrix equation. I hope this is clear to you. So we'll do the other problem, this one, in the next class. Meanwhile, you just take down this figure, and if possible you can do, or else we'll do. Okay, in the next class. Not next class means next week only, because tomorrow I will not be engaging. I have to rest my eyes. This is 3 ampere. This is 2 IS, where IS is this. You can find out the node voltage. Here you can see there are 3 nodes, V1, V2, V3, and this we'll take as a reference node. If possible, try, and we'll anyway do in the next class also. Okay. So that is all for today.